Hey everybody, continuing chapter 5, we're talking about chiral molecules, which we said they have a molecule that has a non-superimposable mirror image, right? It's a mirror image that's non-superimposable. And what's that called? If a molecule has this thing, this non-superimposable mirror image, that's called an enantiomer. A non-superimposable mirror image, right? So if a molecule has an enantiomer, a non-superimposable mirror image, it can be called chiral. Okay, and we also mentioned that there's a couple names for this concept of a carbon with 4 different things on it, and let's remember what those names are. Names for carbon with 4 unique substituents. We had a couple of those names, right? So what were a couple of those names? I'm not going to go through all of them. They were mentioned last time, but Chiral Center is sort of a easy one to remember. Chiral Center, and there's a couple others like asymmetric center and stereogenic center. Okay, so we showed a couple of molecules that have chirality and have this concept of a chiral center or stereogenic center. Let's show a couple more of these. More examples. Okay, so this is a interesting molecule. It has a 6-member ring, but it's kind of not chair form, and the reason is because of the structure kind of forces it out of chair form, and it's got a bridge. See that little bridge on top, and a CH3 down, and 2 methyls up top, 2 CH3s, and a ketone right there. And the name of this is called Camphor. So this is found in a bunch of kind of like over-the-counter pharmaceutical type things. It's found in Bengay, like the muscle relaxation lotion type stuff, and other things like that. So it has that very unique smell that you might be familiar with. So you'd probably know the smell camphor if you smelled it. Anyway, so how many chiral centers are there? How many chiral centers or stereogenic centers are there? So it's a carbon with 4 unique things on it, right? And it's always sp3. And where are they? Well, not the ketone. That's got 3 unique things, right? Carbon, oxygen, and carbon. But like that is a stereogenic center or chiral center. Stereogenic. Remember, stereogenic center is the other word we use. There's a bunch of these names that we give these things. But yeah, that's one. Any more? Is that it? Is that the only one we have? Well, there is this carbon in the back, and you might say, well, it doesn't look like there's 4 unique things because there's like 2 CH2s and a H going back, right? There's an H in the back, right? And then there's a carbon up top with the methyls. But the thing is, these 2 CH2s are different. This CH2 is next to a ketone. This CH2 is next to another CH2. So this is a carbon with 4 unique things on it, and it is also called a chiral center or stereogenic center. Okay, so put little stars there. Okay, cool. What about 2-bromopropane? Is this a chiral molecule? Are there any stereogenic centers in 2-bromopropane? Of course there's not. And you say no, there's not. There's not. That's not a stereogenic center because there's not 4 things around it, right? We have the 2 methyls that are identical. You have a CH, and you have the Br. It's 3 things, right? But what about 2-bromobutane? Of course, now this is a chiral molecule with a stereogenic center, and there is the stereogenic center, right? because there's 4 unique things on there. There's the bromine, the CH, the methyl, and the ethyl. Okay. What about, so this is chiral, of course this is chiral. What about, what about this molecule? So this is it's called plus R limonene. It's all one word, L-I-M-O-N-E-N-E, limonene. This is found in lemons. And it gives lemons the sort of unique smell of lemons. Okay, is it chiral? How many stereogenic centers are there? Okay, so we look for a carbon with 4 unique things. Here we're showing the dash dash dash. That often kind of implies a stereogenic center, but not you can't assume that. But clearly there's 4 unique things on that carbon, right? You have a carbon, you have an H. We're not drawing the H. We have that CH2 next to the alkene. We have that CH2 next to another CH2. So yeah, that is a stereogenic center, and that's a chiral molecule. We haven't discussed plus and R yet. Well, we will maybe this lecture. Plus, what the plus and the R mean. Yeah. Okay. Cool. One more thought. Like if I have this, that's definitely not a chiral molecule, right? And there's no stereogenic centers because that's not a stereogenic center, right? What about that? Well, that is also not a chiral molecule, right? Not a chiral molecule. But what about that? Not a chiral molecule. It's still, there's a plane of symmetry, right? The left side is symmetrical to the right side. So this is a symmetric molecule, right? And okay, so the molecules are symmetric. How could I turn this into a chiral molecule? Well, rather than just add a carbon there and a carbon there, I could just add like 1 carbon. And now clearly we have 1, 2, 3, 4, 5 on one side, 1, 2, 3, 4 on the other. This is definitely now a chiral molecule with a single stereogenic center, right? Because that's not symmetric anymore. Now we have a different amount on the left, different amount on the right. Okay, cool. One more thing. You might say, well, I don't see dashes and wedges on the BR, right? So you might say that doesn't that mean that it's not chiral or something? Well, no. When we draw a chiral molecule, and this is a chiral molecule, but when we draw a chiral molecule but with a line like that, what that is basically implying, what this means is it's a mixture of those 2 things. Okay, so this is a mixture of 2 molecules. Okay. And the 2 molecules, of course, are these 2 things. And what are these 2 things called? Non-superimposable mirror images. What word did we just give this? We just set it up here. Called enantiomers. So these are a mixture of enantiomers. Enantiomers, right? So if we don't explicitly show dashes, like on a chiral molecule, dashes and wedges, then you assume it's a one-to-one mixture of these. Okay, so this is also a one-to-one mixture of 2 enantiomers. A one-to-one mixture of 2 enantiomers. Okay, and another term, one-to-one mixture of enantiomers, has a name. One-to-one mixture of enantiomers. Whenever you have a one-to-one mixture of enantiomers, that has a name. It's called racemic. R-A-C. Racemic. So this is called racemic. Racemic, R-A-C-E-M-I-C. Racemic is a one-to-one mixture of enantiomers, and so if this is a one-to-one mixture of enantiomers, it's called racemic. It's a racemic mixture. Okay. Okay, so we're still on number 1, talking about chiral molecules, and let's consider a reaction. And a simple reaction that you learned in chapter 3, right? So if we take butane, and I'm just drawing the H there, And we do Br2 reaction, heat or light. How many products are there? How many monobromination products are there? How many monobromination products are there? Well, it looks like we have the terminal carbons. This is kind of like one product. And we have the internal carbons. That's like another product. So that's two products, right? We have, we'd say product A and product B, because it's mirrored on the right. So let's just consider the internal one. Let's just, because for the sake of what we're talking about, let's just consider the internal one. Remember also that the odds of primary to secondary to tertiary were 1 to 80 to 1700, right? So the amount of the end product, the terminal products, is actually very minimal. It's really going to be dominated by the internal products. Okay, so I'm going to draw. Well, let's just consider briefly the mechanism. I'm not going to do the full mechanism. We know the mechanism though, right? It's initiation, propagation 1, propagation 2, termination. In propagation 1, actually let's do, propagation 1, of course. I'm abbreviating this a little bit. So propagation 1, right? That's propagation 1. Initiation created the Br dot. Propagation 1 rips off the H. So that's prop 1. Okay? So we're summarizing the mechanism a little bit. There's propagation step 1. Alright, cool. So what does that give you? A radical. Okay. And when this radical attacks Br2, what's the name of that mechanism step? When the radical attacks Br2, it's not prop 1, it's prop 2, right? Okay? Alright, and when this radical attacks Br, it's going to form a new chiral center, a stereogenic center, right? It's going to form a chiral center because when the radical attacks Br, it can either attack from the front, where the Br comes like in the front, or it can attack from the back, and the Br will come to the back, right? And so what are those two molecules? We didn't consider this in chapter 3 because we didn't know about stereochemistry. But in reality, there are two products. One is this. It's actually two products, right? We didn't consider it in chapter 3 because we didn't know about this stuff yet. Okay, so it is going to make two products. And are these the same molecule? Are these like identical? Are they superimposable? Like if I made a model of this and a model of this, would they superimpose on top of each other? Like, are they the same? The answer is no, they're not. Of course they're not. We know that. They're non-superimposable, right? Not only are they non-superimposable, but they're also mirror images. And I can show that again. I'll review how these are mirror images in a second. But yeah, these are non-superimposable mirror images, right? They're non-superimposable mirror images, and that has a name. What are they called? They're called enantiomers, right? So, was this a chiral molecule? Was butane a chiral molecule? Did butane have any stereogenic centers, like a sp3 with 4 things? No, it's not. It's an achiral molecule. That is an achiral molecule. When we react it with Br2, though, it makes a mixture of chiral molecules, right? And the mixture are these two enantiomers. And when this attacks, that's the mechanism, right? We knew that from chapter 3. The mechanism of the radical attacks Br2. When this attacks, and the Br can either come in front, like towards us, or away, like into the paper, what's the distribution? Is it going to be like mostly towards us, or further away, or is it going to be preferred to go one way or the other? Is the Br going to be more this way or more that way? The answer is no. There's no preference at all. These are totally energetically identical molecules. So, and what's that called if it makes a one-to-one mixture of enantiomers? We just gave that word. So we expect a one-to-one mixture of enantiomers. And we just gave it a name, right? What's the name for a one-to-one mixture of enantiomers? Last page. It's called a racemic mixture. Okay, so a racemic mixture is a one-to-one mixture of enantiomers. Okay, so whenever you have a one-to-one mixture of enantiomers, it's called a racemic mixture, or racemic. Yeah. All right. How about let's consider an alternate reaction. So versus propane. Do the same exact thing. So here was butane, and here is propane. So it looks very similar, right? It's also you have a massive preference for internal bromination due to the 1 to 80 to 1700 rule. How many products are there? How many products are there of this reaction? There's two. It's either going to go on the ends or it's going to go in the middle, but the middle is vastly preferred because of the 1 to 80 to 1700 rule, right? So let's just draw the internal product. And actually, to do that, I'm going to also show prop 1. Br dot rips off the H, gives us a radical. Okay. The radical is planar. It's like a, you know, you have an H there. Yeah, it's a planar thing. It's just like it was planar up here. But this then also could now react with a Br either in prop 2, right? With the radical either attacking from the front or the back. And the Br would either come to the front of us or to the back of us, right? And you could say that it would give you two different products, where the Br is to the front of us or where the Br is to the back of us, right? Going towards us or going away from us. Now the question is, are these the same molecule or not? Well, are these chiral? This was chiral, right? This was a mixture of, you know, chiral products that are enantiomers and racemic. Are these, is this chiral? Is there a chiral center? Is that a chiral center? Is that a chiral center? Those are not chiral centers, right? Okay, and also if I took this and I flip it over, it would be that. So these are actually the same exact molecule, right? These are identical molecules, and same molecules. Same molecules. Okay, and it's also, is it chiral or achiral? It's achiral, right? So sometimes you make a chiral product and sometimes you make an achiral product. When we went from an achiral starting material to an achiral product, right? Went from an achiral starting material to an achiral product. All right, and in this case, because you weren't making any chiral centers, you went from a molecule with no chiral centers, achiral, to a product with no chiral centers, and that, of course, is a single product. It's achiral. Okay, whereas up top we started with something that was achiral, but in the formation of it, you know, these are definitely chiral molecules because they have chiral centers. When you made this mixture of molecules, they have a chiral center, and they're a mixture of enantiomers, what's going to be the distribution of them? is always going to be 1-to-1. It's a mixture, a 1-to-1 mixture of enantiomers. So this is a 1-to-1 mixture of enantiomers, all right? So that's a case where we're kind of applying stereochemistry to reactions we know. We don't know too many reactions yet, but this is definitely a reaction we know a little bit about, and this is the behavior, the stereochemical behavior of the radical bromination reaction, all right? Okay, and a big thing to remember is this word racemic. It's a 1-to-1 mixture of enantiomers. Alright, so this leads us, we're still talking about number 1, chirality. This leads us to notice something, that usually the presence of a chiral center or stereogenic center or asymmetric center implies chirality. Implies chirality. I'm going to say in most cases because there will be an exception. For now, that's a general rule. Well, for now we can assume that's a rule, but we'll see the exception in a bit. All right. So usually, if you have the presence of a chiral center, stereogenic center, stereo center, it implies chirality. So the molecule is chiral. Okay. But there's another test for chirality. Another test for chirality that's maybe a little more general, all right, and that is if we have a plane of symmetry, it's either present or not present, right? Not present. So if there's a plane of symmetry in the molecule, and we can show that, and we'll show that in a second. If we have a plane of symmetry in the molecule, if it's present, if there's a plane of symmetry, it's achiral. So if one side of the molecule mirrors the other side, the molecule is always achiral. Always achiral. If there's not a plane of symmetry, if we cannot see a plane of symmetry, it's not present, it's chiral. So that's another way we can kind of consider chiral molecules versus achiral molecules. Okay. All right, so we're looking at the Chapter 5 slides that are on the website. Chapter 5 Stereochemistry. Supporting slides for a mostly whiteboard presentation. We do this from time to time. All right, so this will have a couple slides that are useful for this chapter, Chapter 5. All right. This is the first slide. I'm showing figure 5.4 from the book. I'm going to cover the bottom just as we don't really need to see that right now. But what we're trying to look at is because what we just said is if there's a plane of symmetry that a molecule is achiral, right? So this, of course, is a simple molecule. That's methane, right? And what we're showing is that we can slice methane with a plane of symmetry. So we just put like a mirror plane through methane, right? That's a methane, very simple molecule, achiral molecule, right? And if you slice methane the right way, you can see, oh, the left mirrors the right. Yeah, it's a plane of symmetry, achiral, right? What if we add one thing to methane, like chloromethane, right? Well, if you rotate chloromethane around and you can slice through chloromethane, now we see, oh, the top mirrors the bottom, plane of symmetry, achiral, right? Right. And remember, what did we say generally? Like how many unique things do you need on a carbon to make it chiral? You need 4 things on it, right? All right. So, of course, chloromethane is achiral. There's not 4 things, but we're just trying to show this idea that if you have a plane of symmetry, if you can find a plane of symmetry, it is a achiral molecule. What if we add another thing? So now we'll add another thing, and what do we have now? We have looks like it is 2 chlorines? I think it's 2 chlorines. Yeah, 2 chlorines, right? Okay, so it's actually, we only have 2 unique things on this molecule. We have a chlorine and we have another chlorine. But even if it was a different thing, if it was a chlorine and a bromine, you would be able to find a plane of symmetry. This is just showing dichloromethane, methylene chloride. All right, and when you find a plane of symmetry, you say it is achiral. And the plane of symmetry, there's one right slicing that way, there's one that goes kind of through the middle of it. Okay? And of course, this does not have 4 unique things on it. It's got 2. It's got H and Cl. Alright, so what about if you have 3 unique things? 2 H's, a bromine, and a Cl. Well, there we can see another plane of symmetry, right? That slices right through the bromine and slices right through the chlorine. And then the left mirrors the right. Is it chiral or achiral molecule? Answer is achiral, the same. It's got a plane of symmetry. If you've got a plane of symmetry, you have an achiral molecule. Plane of symmetry, achiral molecule. Okay, so now what if we have hydrogen, chlorine, bromine, and fluorine? Well, this does not have a plane of symmetry. There's no way you can slice through this and get like 2 equal parts. Is this chiral or achiral? This is a plain old chiral molecule with a single chiral center or stereogenic center. Okay, so that's what I wanted to show. This slide shows that nicely. It's also in the book, of course. The idea that if you have a plane of symmetry, if you ever have a plane of symmetry in a molecule, it automatically makes it achiral. If you have a lack of a plane of symmetry, then it would make it chiral. And what's weird, and we'll see this in a second, is that there are cases where a molecule will have a chiral center, well, like 2 chiral centers, we'll say. Well, there will be cases where a molecule has like 2 chiral centers and still have a plane of symmetry, and the plane of symmetry makes it achiral. And that's a little weird for students to see. We'll see that in a second, all right? But this is definitely chiral. 1 chiral center, no plane of symmetry. It's a chiral molecule. Alright, so we just basically said this and we showed it with a nice figure, that if you have a plane of symmetry, molecule is always achiral. If you do not have a plane of symmetry, the molecule is always chiral. Sometimes it's a little hard to see the plane of symmetry, sometimes it's a little easier. We'll see some examples of identifying planes of symmetry. Alright. I think this is a homework problem, HW55. Draw structures of dimethylcyclobutane. Dimethylcyclobutane. So cyclobutane with 2 methyls, and figure out which are chiral, which are achiral. Which are chiral, which are achiral. So let's draw some of these. Just cyclobutane with methyls on them. Okay, so how about that? Alright. Is that a chiral molecule or an achiral molecule? I mean, seeing the wedges and dashes, sometimes people say, well, that implies it's chiral. That's not always true, though. The wedges and the dashes don't necessarily imply that. Do you see a plane of symmetry? Like, if I put a mirror plane right in the middle, does the left mirror the right or not? Well, it doesn't, because if I put a plane of symmetry, well, one methyl's coming towards us, one is going away. This is chiral. Okay. And what if I do this? Is that chiral molecule or achiral molecule? Well, kind of looks sort of like the other one, but it's not. These are not the same molecule, right? This is chiral. What's the relationship of these two molecules? They actually look like mirror images, and they are, and they're non-superimposable mirror images. So, because if you have a mirror image of something, it could either be superimposable or non-superimposable, right? If a molecule is superimposable on its mirror image, then it's the same molecule. Then the molecules are identical. These are mirror images. But how would he know this is not superimposable? Because if I took this and flopped it over, if I took it and flopped it over, it would be a different molecule than this. It would actually look exactly like this. If I took this and flopped it over, it would look exactly like this. Those are not the same, right? So these are non-superimposable mirror images. And what's the name of that? They're called enantiomers. Those are called enantiomers, right? Non-superimposable mirror images. Okay, so what about if I have a different one, another stereoisomer? Well, that's weird. Now it looks kind of like the left mirrors the right. And if I put a mirror in the middle, I'd say, well, the left does mirror the right, right? Does that make it chiral or achiral? Makes it achiral. It's a weird, and the other thing about this, it's even maybe weirder, because we have chiral centers, right? Let's draw the chiral centers. We got chiral center, chiral center, chiral center, chiral center, right? We have chiral centers. All of those are 4 carbons with 4 unique substituents. These are chiral centers. These are chiral centers. By the definition of chiral center, what's the definition of a chiral center? Is if you have 4 unique substituents, right? They do. You have a CH3, you have an H, you have a carbon with a methyl on it, and you have a CH2. That's 4 unique things. And that is a chiral center, just as that is a chiral center. Those are both chiral centers. But the net molecule is achiral, and that's because the left mirrors the right. You have a plane of symmetry. Achiral, okay? What about another one? Achiral. Of course, that's achiral also, and that's because there's no chiral centers at all. That is not a chiral center now, because now that's a carbon with 2 CH3s and then 2, CH2, CH2, and the CH2s are all they extend back to the other CH2, right? There's no difference between this CH2 and that CH2. All right, so that's an achiral molecule. Of course, any more we can draw? Chiral or achiral? Chiral or achiral? A simple test for chirality is also presence of chiral centers. If you don't have chiral centers, it's definitely achiral. Just like this did not have chiral centers and it was achiral. There's also a plane of there's ways to draw the plane of symmetry, right? Because the methyl is coming straight away towards us, and the other methyl is going straight away. I can slice it like right through the middle, basically. But anyway, it's achiral. This one, do you have any chiral centers? No chiral centers. That's not a chiral center. That's not a chiral center. No chiral centers, right? No chiral centers, and also a plane of symmetry. Because if I slice right through one CH3, right through the ring, right through the other CH3, then the top mirrors the right. If you have a plane of symmetry, is it chiral or achiral? That's achiral. Any more we can draw? Is that chiral or achiral? It's very similar in concept to this one. No chiral centers, plane of symmetry, it's achiral. Okay. More examples. Alright, let's consider this molecule cyclohexanol and try to determine is it chiral or not. Is cyclohexanol chiral or not? And you can pretty quickly just say, well, there's no chiral centers, right? That's not a chiral center. That's not a chiral center, is it? It's not a chiral center. Because there's how many unique things are on the carbon? There are three unique things. There's a H, there's the oxygen, and then there's CH2s wrap around. So not a chiral center. It's definitely achiral. But let's try to visualize the mirror plane in this molecule. Because if it's achiral, there should be a plane of symmetry, a mirror plane, right? A plane of symmetry. How can you see that? And the thing about cyclohexanol and cyclohexanes is they adopt a certain conformation that you should be familiar with, right? What's the conformation that we know? Cyclohexanes? It's the chair conformation, right? So that we should draw this as a chair. I actually did that already, and we can see it right there, and just kind of cut to the chase a little bit. I drew out cyclohexanol. There we are. So let's try to envision where the plane of symmetry is, okay? Because there should be a plane of symmetry that slices this molecule into two equal halves. And there is. The plane of symmetry goes right through that CH2. It slices through it, like kind of like vertically. It's a vertical slice. And that slices right in between these two CH2s, right? Those two CH2s. And then it slices right between these two CH2s. And then it slices right through that carbon, and it slices right through the oxygen, and it slices right through the hydrogen. So that is a nice plane of symmetry that slices us through this. Every achiral molecule has a plane of symmetry. Sometimes it's a little tricky to find. Sometimes you have to kind of look at it a little bit, but this is a nice example, okay? I would copy this into your notes nicely and try to visualize where the plane of symmetry is. You could also make a model of this with your model kit. For the oxygen, you could just call it like, you could do this with ethyl too, like make it like ethyl cyclohexane. Also, the same kind of thing. You're going to see the plane of symmetry if you don't have colored model like oxygen, or you can just do red for oxygen, white for hydrogen. But you can definitely see the plane of symmetry in a molecule like this. All right. What about this molecule? Chiral or achiral? This molecule, chiral or achiral? And we definitely see what appears to be two chiral centers. That's a requirement for chirality. And we don't see a plane of symmetry, because if you mirror the left onto the right, it's different. This is not a plane of symmetry, so this is a chiral. Right? But if we had this molecule that kind of looks sort of similar, chiral or achiral, the answer is that this has chiral centers. So you might say, oh, that makes it chiral, but that does not make it chiral, because the left mirrors the right. There's a nice plane of symmetry right through the molecule where the left mirrors the right. This is achiral. Okay. And real quickly, I'm going to give this idea, this concept, a name also. So if you have chiral centers, which we do, we have chiral centers. We have chiral centers, but a plane of symmetry. But you also have a plane of symmetry, right? That makes it achiral. The net molecule is achiral, even though you have chiral centers, right? You have chiral centers, but a plane of symmetry. The net molecule is achiral. We're going to give this a name. It's called meso. M-E-S-O. Another word. So meso is going to be the situation where you have chiral centers and a plane of symmetry, and the molecule is achiral. Meso. Okay. So we could say this is achiral meso, or this molecule is achiral and it's meso, right? It's achiral and it's meso. Achiral meso, right? Meso refers to that requirement of a plane of symmetry, but you have chiral centers. Meso. Is this guy meso? Is cyclohexanol meso? Does this have chiral centers and a plane of symmetry? It has no chiral centers, but it has a plane of symmetry. So this is what we call a chiral non-meso. All right. So there's kind of two types of achiral molecules, right? Achiral meso refers to chiral centers, a plane of symmetry, and net achirality. But you can also be achiral non-meso, where you just don't have any chiral centers, right? Achiral non-meso, no chiral centers, and it's also achiral. So if I have ethanol, is that chiral, achiral meso, or achiral non-meso? Is it chiral, achiral meso, or achiral non-meso? Is it chiral, achiral meso, or is it achiral non-meso? First, is it chiral? Any chiral centers? You see any chiral centers there? No, it's not chiral. Is it achiral meso? Well, in order to be achiral meso, you'd need chiral centers, and you would need a plane of symmetry. It says no. So that must mean it's a achiral non-meso. Okay. How about this? What as a fourth option? It's definitely achiral non-meso, right? Could it ever be chiral and meso? Could it ever be chiral and meso? The answer is never. Never. It can never be chiral and meso, because in order to be meso, it has to be achiral. Meso implies achirality. So this, sometimes on my exams and quizzes and stuff, I have this be an option, like, oh, is it chiral and meso? And the answer is it's never. Nothing can ever be chiral and meso. Meso implies achirality. Okay? Alright, so this is a nice example too. Okay, and we're still on number 1, which is chiral molecules. A lot of kind of introductory material. We're still just kind of, but we are learning a lot, I think. We're covering a lot of ground, but we're still technically on what I'm calling number 1 here. And I showed this before, let's show it again. There are 2 ways to draw enantiomers. There's actually more than 2 ways, but certainly when you're learning this, you just want to be able to draw the enantiomer easily. There's a couple, well, kind of 2 ways that I think stick out. All right, so let's draw this molecule, 2-fluoro, what is it, 1, 2, 3, 2-fluoropentane, right? 2-fluoropentane, is that chiral or not? Definitely chiral. You have a chiral center, there's no plane of symmetry, it's very, 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 very chiral. And if it's chiral, it has a what? When a molecule is chiral, it has an enantiomer, right? And so I often draw what looks like a resonance arrow, but it's not resonance. And I say En for enantiomer. And you can draw the enantiomer just by drawing the mirror image, right? That is clearly the mirror image. That is, this and this are mirror images. You can see, oh, there's the mirror plane. Those are mirror images. But this is not a superimposable mirror image. These are unique molecules by the definition of an enantiomer. They're unique molecules. If I took this and flopped it over on top of this, you'd see, oh, they're not superimposable, right? These are not the same molecule. And so what I often do when I'm saying here is there's two ways to draw enantiomers. I can draw it this way, which shows the mirror relationship, that they're mirror images, but I can also take this and flop it over, and now it kind of looks like the left molecule. It kind of looks like this, right, where the F is coming towards us, but if I took this and flop it over, pull it out, flop it over, I take it out, I lift it out of the paper, lift it, flop it over. Now it looks kind of like that, but now the fluorine's there, right? And if I took it and flipped it over, here it's coming towards us. Where's the fluorine going now? It's going away from us. So these are the same molecule, right? And they are both, you know, the same identical molecule. These are the same molecule. I just took this, flipped it over, and I get this. And now, and I'm claiming that these molecules, which are the same molecule, are the enantiomer of this, right? And now you can see, oh, look at that, look at that. Yes, it's clearly the configuration of the fluorine is the opposite, right? And that's what you expect with an enantiomer. So yes, that's what I'm trying to say is there's more than two ways. I just happen to draw these two ways. One that shows the kind of mirror relationship, the other that keeps everything aligned. This is aligned with that, right? This is aligned with that. But you can see the configuration of the fluorine's opposite. All right. Okay. Let's show another example of that. This is just a basic idea of drawing chiral molecules. Before we continue, all right. So chiral or achiral? Chiral or achiral? Well, I mean, is that a chiral center or not? Looks like it's a chiral center, right? It's sp3, you have 4 unique substituents: bromine, hydrogen, CH2, benzene, right? Yeah, it's chiral. Chiral molecule. And if it's chiral, it's got a what? Enantiomer. And I can draw the enantiomer in multiple ways. I'm going to focus on 2 ways, though. I'm going to draw the kind of mirror image relationship, just like I did up here. And how would that look? It kind of looks like, now the benzene's on the right. That's a 5-member ring, right? 5. Right? You can kind of see the mirror relationship. Let me make it a little nicer there. Okay. Yeah. They're enantiomers. Very clearly they're mirror images. But what's the other way I can draw this? And I think an alternate way to show the structure of the enantiomer will be to, don't forget your benzene, to look kind of like that, but focus on maybe the different configuration of bromine, right? Take this and flip it over. Take the enantiomer, flip it over on itself, flip it over. Now the benzene's on the left, and the 5-member ring's on the right. Now the bromine was coming towards us, now the bromine is going away. Cool. So now these are the same structure. I just took it, flipped it over. But if I look at this versus this, it's like you can very clearly see that they are opposite, right? This shows the mirror image relationship. This doesn't necessarily show the mirror image relationship, but it does show the different configuration of bromine. So hopefully that's useful as just another way to kind of draw how enantiomers look. Okay? All right. So now we're actually on to number 2. Moving along. I think we've learned a lot about chiral molecules so far. There's some other things we got to talk about. Number 2 is a unique topic. It's called optical activity. Number 2 is called optical activity. Optical usually means something about light. Activity means maybe an effect on light or something that the effect of chiral molecules on light. And that's a summary of what we're going to talk about. Alright, so let's consider a pair of enantiomers. Let's consider a nice pair of enantiomers. Make it easy. 2-bromobutane. Chiral molecule, 1 chiral center. Right, En for enantiomer, and that's one way we can draw the enantiomer. Just keep it all lined up and just show, oh, the Br is going the other way, right? Those are enantiomers, right? We could also draw, like we just did, we could draw, right, this and this are the same molecule. These two kind of show us the mirror relationship, but I like to usually keep it aligned, keep the molecules aligned, and then just focus on a different configuration of the chiral center, right? All right, enantiomers. Do we expect any different physical properties? Do we expect different physical properties of those 2 enantiomers? Like if I have a bottle of this and a bottle of this, and I'm trying to analyze them and look at the different physical properties. Do they have different physical properties? Like if I take this and I take this and I do some measurements, what's the difference? Like for example, is there any differences in boiling point, do you think? Like I boil them, is that going to boil higher or lower? Probably not. Those are going to. How would this affect boiling point? The structure like this, it's not going to affect boiling point. What about melting point? Do you think, like if I freeze them, I freeze that. Do you think it's going to affect the melting point? The configuration around bromine, is that going to affect melting point? The answer is no. What about density? It's like the grams per volume, right? The density, mgs per mil or grams per milliliter or something. Grams per liter. Is that going to be affected? Do you think the density is different? Absolutely not. What about the heat of combustion? We talked about that. It's property, right? You burn it and get the energy out. Is that going to be any higher or lower energy than that? Very unlikely. The only difference is the three-dimensionality of the bromine, right? Okay, so no difference there. There's no difference in any of these things. The bonding, the energy, etc., is all identical in the enantiomers. Sorry, I wrote that high. Okay, so bonding energy, etc., is all identical in the enantiomers. There's no difference in the enantiomers. So is there any way to distinguish the enantiomers, like through a experimental technique? can I distinguish that from that? I certainly can't use things like boiling point, melting point density, etc. Okay. All right, but there is a key difference, and otherwise, you know, what would optical activity mean then, right? There is a key difference. Key difference between enantiomers. There is a key difference between enantiomers, and the difference is the behavior in plane polarized light. The difference is in plane polarized light. There's also smell. So sometimes things smell differently. So I think we talked about Carvone. I think it was Carvone. Yeah, Carvone. I think it was. Remember Carvone? That was a structure where there's two enantiomers. One smells like caraway, and the other smells like spearmint or peppermint. It's very weird. If you really smell them, it's like they smell like completely different things, but they're just enantiomers, right? And so, why would we smell enantiomers differently? I'm pretty sure these smell like nasty chemical, so neither of these would smell really different. But Carvone is an example of enantiomers, and why would they smell differently? It's because our nasal receptors are chiral. Proteins are chiral, right? And so when you smell things, and one enantiomer will bind to the receptors different than the other enantiomer, right? But anyway, let's focus on this plane polarized light thing. It's kind of a pretty cool story. And okay, so plane polarized light. The behavior, and I'll show the nice figure of this in a second, but the behavior is going to be called optical activity. What we're going to see is that enantiomers will actually rotate light. They rotate the light, and we can observe the rotation of light. And it's called optical activity because we're causing a difference in behavior of light between the two enantiomers. And then enantiomers are called optical isomers. It's another name for enantiomers. Optical isomers. So these the two enantiomers will be called optical isomers. Okay, so let's keep going with that. Okay, so I'm going to show a figure that kind of that describes this a little bit. All right, one sec. Okay, so before I show my handout, I'm going to mention a little more about this. So what we're going to find is that the enantiomers rotate light, rotate this stuff called plane polarized light. Plane polarized light. It's a special kind of light. It's just, we have a polarizing filter. Enantiomers will rotate plane polarized light in different directions. Okay, and if it rotates to the left, then we're going to call it minus. If it rotates the light to the left, it's going to be called minus or levorotatory. Okay? And if it rotates light to the right, it's going to be called plus, and that's going to be called dextrorotatory. Okay, so I think from Latin, laevus is left. And dexter is right. I'm not a Latin expert, but that's kind of where those levorotatory and dextrorotatory come. Okay, so let me show this handout and figure 5.5, which shows exactly what's happening with this plane polarized light stuff. Alright, so this is the figure I showed earlier. You know, we talked about the planes of symmetry and stuff, right? Remember that? Well, if you look at the bottom, this talks about optical rotation and how the instrument kind of works. So let's go through it. Basically, you have a light source. This is basically a special light bulb. And that generates light that's normal light. It's oscillating in all planes. So the wavelengths are kind of going all directions. You apply something called a polarizing filter. And actually, some sunglasses are polarized sunglasses. So they have the same kind of thing. So polarized sunglasses are essentially what this is. And what that does is it filters out all of the wavelengths in all the different orientations, except like one angle. Okay, so you have light that's going up and down, up and down, up and down, and the wavelengths are going up and down. And then you have your chiral molecule, like 2-bromobutane. All right, single enantiomer of negative 2-bromobutane. And what that does, and this is to me a mystery. I don't really totally understand the physics of this, but the molecule and the chirality of it rotates the plane polarized light. In this case, minus, which is negative, and to the left. Minus is left, right? Levorotatory. So the filter, I mean the light, is actually rotated as it goes through the 2-bromobutane, right? Now we have a new angle, and all we do is we have a different analyzing filter that we can rotate with our hand. So we just rotate it and we find it where the light is coming out, and that gives us an angle. Okay, it's called alpha. So that's the rotation. That's the angle of rotation, and so we're like, oh yeah, well we've determined the amount of rotation, and then there's just a little formula we apply, and we get a number out, and you know, we're looking through this, and we just rotate the little lever that controls this. It's pretty cool. It's a easy way to measure the angle of rotation of a pure enantiomer, and the net behavior is called optical rotation. Okay, book talks a bit more about this. You don't need to know that much about it. Just understand that pure enantiomers rotate light. Pure enantiomers rotate light, and these are often published values, the numbers that we can look up. What do you think would happen if you have a 1-to-1 mixture of minus 2-bromobutane and plus 2-bromobutane? What do you think would happen to the light? Nothing would happen. The rotation would cancel out, and that's so. If you have a racemic mixture, like a 1-to-1 mixture of two enantiomers, yeah, you'd expect a canceling effect, and then there'd be no rotation. Okay. Okay, so we talked about the principle of optical rotation. We're still on number 2, right? Continued optical rotation. Other little tidbits about optical rotation. What do you think that instrument's called? That measures optical rotation. The instrument is called a polarimeter. Polarimeter. It's kind of a classic chemistry analytical method. Polarimeter. What does the machine do? What does it do? It generates plane polarized light. Generates plane polarized light, and it allows us to measure rotation. And is the rotation to the left or the right? Well, it could be left if it's minus, or right if it's positive. Okay. That's an angle. We get out obtain an angle. The angle is the amount of rotation. Okay. I think we mentioned this already. Let's mention it again. The behavior of this is called optical activity. The behavior of chiral molecules rotating light is called optical activity. And enantiomers are sometimes called optical isomers. Right? So if I have my two enantiomers that rotate light in different directions, sometimes they're called optical isomers. Right? And what else? The output of the polarimeter, is called the observed rotation. Observed rotation. And it's alpha, right? Alpha. So the value we get is called alpha, and it's called the observed rotation, right? Now we take the observed rotation and we normalize it. We apply a little bit of formula, and that gives us a universal measure. So let's just show that. This is not on the exam or quizzes or anything like that. It's just, you know, we just got to understand what's going on with this rotation. So let's show that. One second. So we normalize alpha rotation, and by normalize I just mean we apply a little correcting formula. We normalize to a universal value. We normalize the observed rotation to be a universal value that is called the specific rotation. This is done in science a lot. We'll we'll measure something and then we'll apply a formula so that we have a universal number that's used throughout the world. And specific rotation is that. And so what is specific rotation? It's bracket alpha D, as in dog, 2.5, 2.5, and this is equal to the observed rotation, alpha, divided by L times C. What are these different things? L and C. Okay, so D refers to the sodium emission D line, Na emission D line. All this means is it's a specific wavelength of light. So it's lambda is equal to 589 nanometers. That's what D means. All it means is it's a specific wavelength, a specific wavelength of light. Okay. Yeah, 2.5. This is the temperature, right? 25 degrees temperature. Temp. Okay, that's easy. We got the temperature. We're using a very specific wavelength, and to be universal, we need to be, be consistent, right? Alpha is the observed, OBS, observed, right? L is the path length, So you have a little tube of sample and you put it in the polarimeter and you rotate it around, and the path length is just the distance or the length of the solvent solution, the solution of your chiral molecule. So this is measured in decimeters. It's like 1 dm. What's a decimeter? I mean the standard path length is 1 decimeter, which that's 10 centimeters, right? This is the only instance in science that I know where decimeters is actually used, because nobody uses decimeters. You always talk about centimeters or meters or whatever, but this is a case where they measure it in decimeters. Okay, and then this is the concentration in grams per mils. Okay, so given all this, this becomes a universal value, and you can compare it between substances. So let's show a couple values, and then I think we're probably ready to stop. Okay. And you're never going to do this kind of, you won't do this calculation. You need to just be familiar with the basic idea of this. Okay, so you're not going to be calculating these alpha values or anything like that. All right. So let's maybe I'll start and we'll stop. I'll just show a couple of alpha values, then we'll continue next time. So example molecule. I'm gonna do a fresh sheet. Okay, so molecule alpha D25. Okay, so what are some molecules? We'll do 2-bromobutane, and it's negative 23.1. Is that negative, or is this going to be a minus molecule or a positive? In terms of the name, the minus means left, and this is the name of the molecule is over here. This is minus 2-bromobutane. Minus 2-bromobutane. So the minus here means negative rotation, right? Minus 2-bromobutane. Okay. And this one looks like what? What's the relationship? It's the enantiomer, so it's going to be 23.1. And this is going to be plus 2-bromobutane. So the plus means right direction rotation. Let's draw alanine. Alanine. Remember Alanine? It's one of the amino acids. It's chiral. It's got a chiral center. There's a CH3 and an H. Alanine is 8.5. And this is called plus alanine. What does the plus mean? It means positive rotation. Okay. Alright, so we just finished a couple optical rotation values, and we'll show a couple more next time and then move on. There's a couple more topics to do in chirality. Hopefully things are starting to make sense, and definitely come by and ask some questions in office hours. Alright?